Okay, this is part 2 of a 2-video series on Extrema, specifically absolute extrema. So if you didn't watch the other video, that one should be watched first. That introduces you to the concept of absolute extrema. And now we're going to get into the nitty-gritty, how do I find it, and go through the process. So I'm going to go through three examples here. And while we're at it, we might as well give ourselves some challenging functions. So I think these are going to be good ones to work through. Make us think a little bit in terms of derivative, because we will be doing some derivatives here, and not things that you can just picture in your head. So question will be phrased as find the extreme values of the function on the given interval. Whoops, and the interval will be given to you. So I forgot to write that in here. So for this particular one, 0.5 is less than or equal to x, which is less than or equal to 4. Consider that the given interval. That could also be written this way if you're more familiar with interval notation. Other ways that this question could be phrased, just so we're familiar with any way that this could be thrown at us. It could be find the absolute extrema, absolute minimum or maximum. I'm actually going to propose that they might not put the word absolute. So they could just say find the minimum or the maximum of the function. And it is assumed if they don't specify relative minimum or maximum that we're talking about absolute. And that's where I think this one gets tricky, is a lot of people just miss the concept and don't realize they're supposed to be finding an absolute. Okay, so I sort of mentioned in my last video that we're going to throw out the number line analysis when we're doing absolute, only because it's not going to give me enough information. So if I were to do a number line, it's worth considering. If I were to do a number line and then figure out where my derivative is 0, and I get certain points where my derivative is 0, and then I figure out my function is increasing, decreasing. I know I have a minimum here, but then if my function decreases again, because my derivative is negative, now I don't know which one is the minimum until I find y values. So the key with this is we actually need to evaluate the function at specific points, but we don't want to just evaluate it at any point. And we really don't even want to just use the table. I know that your calculator has the ability to calculate a maximum right on the graphing screen. And that's a great way to check your work here. But folks, you got to understand this is going to be a no calculator question for sure. And they're going to make it something that so I'm going to give you ones that are going to be decimals until we get to the third example. But I would say that they will make it something that you are expected to do completely by hand to hold you accountable for understanding this. Okay, so what points are we going to consider? What are these special points that we're going to consider that could be possible extrema? Well, we want to consider all the relative extrema. So those would be the critical points that we've been talking about. And then we just want to add the endpoints in and consider those as well. So let's start by finding our critical points. So hopefully you're remembering how to find critical points. And let's just go ahead and walk through it. So critical points where my derivative is equal to 0 or undefined. So I'm going to start with, let's find the derivative, which means I'm going to start with actually rewriting my function. So back up, I'm going to rewrite the function as x to the negative second plus natural log of x. Now I'm in a good position to take the derivative. So y prime is negative 2 x to the negative third plus 1 over x. It's been a while since we've done the derivative of natural log of x. And that gives me negative 2 over x cubed. Whoa. Plus 1 over x. In terms of thinking about setting that equal to 0, I'm not loving it. So I'm trying to figure out what's undefined. I don't like the fact that there are two fractions. So I'm going to do a bit of algebra here to tidy it up and make it easier for my brain to think about. So let's get some common denominators here. Multiply by x squared and x squared. And that's going to allow me to say I have negative 2 plus x squared all over x cubed. That's a nice derivative to work with. Okay, so I need to consider two places where it's equal to 0 and where the derivative is undefined. So at this point, I'm really just considering where am I going to have relative extrema. Remember, equal to 0 would be something like my graph is turning around, slope is equal to 0. Undefined might be a cusp, something like that. If I'm thinking visually what could be happening on my graph. So derivative equal to 0 is going to be for a rational function when the numerator is equal to 0. You can set the whole thing, and then multiply by x cubed is going to cancel out on both sides. So I'm going to go ahead and just go with that. Put the -2 plus x squared equal to 0. That's going to give me x squared equals 2, which gives me x equals positive negative square root of 2. I'm noticing that the negative square root of 2 is outside of my interval. So the only one I'm going to carry over is the x equals positive radical 2. And then I can't forget about the undefined case. The derivative is going to be undefined when your denominator is equal to 0, because the dividing by 0 is undefined in math. X cubed equals 0, which means if I take the cube root of both sides of that, that's going to give me x equal to 0. And that is outside of my interval, so that's actually not going to carry over, even though that is a critical point. So depending on what the interval is, I can have more or less numbers on my table. There's no magic number of things, values that I will have, excuse me, have on my table. So now I'm just going to make a quick little table here to compare. So I'm going to put my significant x values in my table, which are going to be any critical points and endpoints. So I'm going to start with my endpoints, 0.5 and 4. EP, I'm just labeling those as endpoints, so I know why I have them. And then we're going to add the radical 2 from here, and that's my critical point. And then I'm going to figure out my y values. So this is literally just me evaluating my function, which you've done numerous times when you graph things, a skill that you're familiar with. And like I said, most likely you would be asked to find this without your calculator. This is not one that we will be able to do without our calculator. So go ahead and grab your calculator, and let's not waste a ton of time trying to figure out the natural log of something. Unless it's a value with e, we're not going to be able to do it in our heads. So I would literally be doing one of two things. You could type your function into your y equals and then calculate multiple values. Or you could obviously do 1 over 0.5 squared plus natural log of 0.5. And I'm getting 3.307. Good time to remind ourselves that we are going to always round to 3 decimal places. So go ahead and pause the video, grab the other two numbers, and then we'll pick up. Okay, so those are the values I'm getting for my 3 values that I'm testing. And now we're at the point that we are ready to, and I should have been following along with that note sheet. If you have the steps in front of you, I am following like what I would consider 4 steps. You can decide how many steps you want to make this process. We found the critical values. We're evaluating f of x at each critical number, important to this problem, so within the interval. We're evaluating f of x at each endpoint, so steps 2 and 3 are make the table. And then we're just comparing, and we're literally looking for the highest and the lowest. So it looks like this one is the highest, and it looks like this one is the lowest. So we have the absolute max, absolute min. What about this one? Not important. What that's going to end up being is a local extrema. So let's take a quick sec and graph this function and just double check that this makes sense. I gave you some visuals before we even did any examples. And let's just see what's going on with this, because like I said, this is not a function that I expect you to know in your head. So it turns out the function looks something like this. And the values that we were looking at, 0.5, radical 2, and then 4 somewhere over here. So let's make sense of this. My absolute maximum here, highest point on the graph. My other endpoint, so I guess I shouldn't have put arrows there because we're chopping off this function, these points. So the other endpoint over here is higher than my minimum point, but not as high as my left endpoint. So this is a relative maximum, but just not as high as the other one. And then my other, my critical point ends up being the minimum, absolute minimum. So my 2 answers would have been right here, the really important to remember, and this is next to the table on your note sheet, is that the absolute maximum or minimum, the values, when they talk about these values here, they're meaning y values, functional values, y values, not x values. Unless it's specifically said where does the maximum or minimum occur, your answer is always going to be a y value. One of the most misunderstood parts of these questions. So we just have to get used to that wording. Okay, let's do a second example. You've got the process now, so now it's just a matter of, like, let's look at some other weird examples. So I'm going to go a little bit quicker this time. Trying to pick really weird ones for you. How am I doing? I'm also not writing legibly. Okay, so you know the drill. We need to find the critical points, and then we're going to make a table of values, compare the critical points and the endpoints as far as the functional values. So first step is, let's do some calculus. Just my power rule, 4/5 minus 1 is going to be a negative 1/5. What a beautiful derivative. X to the 1/5 in the denominator becomes 5th root of x. So taking my derivative and considering when is f prime equal to 0 and when is f prime undefined. So equal to 0 when my numerator equals 0, which does not happen, so I just don't have any critical points there. Equal to, or undefined, when my denominator is equal to 0. I can divide everything by 5 there, and I get 5th root of x has to be 0. Take everything to the 5th power, and we get x equals 0. Okay, you might have just thought through what can I put in there to get a 0. So x equals 0 looks like it is my only critical point. So on my table, I'm going to get my x values, and I'm going to go ahead and put that x equals 0 critical point in there, and then include your endpoints. So my endpoints are -3 and +4. And now I'm going to do some calculations here. So going back to my original function, and I don't know if I mentioned that in the last video, going back to this function when I'm doing my calculations, not using the derivative anymore, and that's different. When we're doing our test values with our number line and trying to find the signs, we were plugging into our derivative. Totally different concept. We want y values to compare. So f of -3 is -3 to the 4/5 power, f of 0. So I know that's 0. The others I'm going to plug into my calculator to get some y values. Okay, and then my question to you is, what are the answers? So we were trying to find the absolute extrema. So we're looking at highest and lowest. So it looks like 0 is my lowest. I'm just comparing those 3 y values that I have. And 0 is my lowest, so I'm going to say that's the absolute minimum. And 3.031 is my highest, so that's the absolute maximum. And this is a trick because one of those is wrong. So which one is wrong and why? Yeah, okay, so if you notice, there's something different about my interval there. And if you were real observant, you might have noticed it. If not, trying to make a point here, so follow along with me. I've got a less than, strictly less than, not less than or equal to symbol. Another way of writing that, if you want a different way of seeing that, would be to say that we have the interval -3, including -3 to 4, open, not including 4. That is not a closed interval. Therefore, I can't guarantee that there's both an absolute maximum and an absolute minimum. So what's happening here, because my right-hand endpoint of 4 is not really an endpoint. That's an open interval. The function never reaches x equals 4. Therefore, it never reaches this value here of 3.031. So what's the highest value I get to? 3.030? We can't really say. We're just approaching that value. Now, it also would be inappropriate to say that this is an absolute maximum. This is a relative maximum. But clearly the function is going to get higher than 2.408 because it's going to reach somewhat close to this. We just can't say it's going to reach that because it's an open interval. Okay, you could certainly look at this graphically, and this is going to look like some of those graphs that we were randomly looking at, where we've got, so graph looks somewhat, I don't have a great picture here, and I don't want to take time to graph it, but you please, if you already have the function in your calculator, go ahead and graph it. It looks something like, whoops, this, probably not to scale, and at -3 over here and 4 over there. So this is a closed point, this is an open point. So graph is getting higher on the right hand side, and something even like here as I'm approaching 4, maybe that's 3.9, this point has a higher y value than this point over here, this relative maximum. So we can't say that 2.408 is the absolute maximum. We also can't say that that's the absolute maximum because of that open interval, the fact that I have not given you a closed interval. Therefore, we say absolute minimum of 0, no absolute maximum. Okay, so that would be my final answer. I know, trick question. As soon as I change that to a less than or equal to and made it a closed interval, now you would have both an absolute minimum and the absolute maximum would have been the 3.031. Okay. Okay, hopefully you're having some fun with these. We're going to do one more example because I want to give you sort of a true picture of what this would look like as a no calculator question, and also give you an idea of how we could have multiple critical points that we need to consider. So we start the same way we started all the other ones. Let's do a derivative. Pause the video, try to finish that derivative. Hopefully you recognize that that was a chain rule. Yep, good old chain rule coming back to haunt us. So I'm thinking of that. I have something squared. So remember, I like to write that as cosine x quantity squared, and maybe that helps you think through derivative here. So I'm thinking I've got u squared, and u is cosine x. So we've got 2u, derivative of cosine is negative sine x. So putting that together, I've got 2 times u, which is cosine x, times negative sine x. Or I should write that as cosine x minus 2 sine x, cosine x, in whatever order you want to write that. And then your favorite thing to do, factoring. This is a good example of a weird kind of factoring. We're much more used to factoring polynomials. What can I factor out here? Well, I've got 2 terms. Cosine x, that's all there is there. So let's see, the second one does have a cosine x. So I can pull the cosine x out. And then I'm left with 1 minus 2 sine x. So why did I take the time to factor that? Well, because the whole point of me finding the derivative was to find critical points. And we should be getting used to and more comfortable with what a critical point is, where my derivative is equal to 0 or undefined. So I could have waited and factored after I did that. I'm now going to consider both cases. One is f prime equal to 0, and one is f prime undefined. So as soon as I set that derivative equal to 0, that's where I'm going to want the factored form. So like I said, you could have just set this equal to 0 and then factored. I just went ahead and factored because I'm kind of got that drilled into my head. So now I can set both factors equal to 0 is the beauty of this. So just the same you would if you had x plus 2 and x minus 3, and you would set both of those equal to 0 to get your 2 factors. Same thing as that, just not a polynomial. So let's set both of those equal to 0, and I've got cosine x equals 0, 1 minus 2 sine x equals 0. Wow, it's been a while. So when is cosine equal to 0? Yep, I'm thinking the unit circle. Draw it if you need to. Cosine is my x value, so it's not over here. That's when cosine is 1. Cosine is equal to 0 up here, which is pi over 2. And I'm on the interval from 0 to 2 pi, so I got to keep going. It also happens down here, and that would be 3 pi over 2. So those are my first two critical values, pi over 2 and 3 pi over 2. And then I'm going to keep solving here, so I'm going to get 1 equals 2 sine x. Add the 2 sine x, divide by 2. So I'm asking myself, when is sine of x equal to 1/2? That would be what angle gives me a sine value of 1/2. So now I'm thinking of sine being 1/2. Sine is your y value. So the way I like to think of that is that's the short side of the triangle is 1/2. It has to be a positive, so I should be in my first and second quadrants. And that should be pi over 6. Not pi over 3. Pi over 3 would be cosine is 1/2. And then my pi over 6 in my second quadrant is 5 pi over 6. Good thing I only gave you the interval from 0 to 2 pi, right? The other pi over 6, by the way, would be down here, and here would be negative sine values. That's why I'm skipping those. Whoa. So without even considering the endpoints, I have 4 critical points. Putting that together, I'm going to have 6 values I'm putting in my table. Give yourself some room. We're going to make a gigantic table right now. And I'm going to start with, of course, my 0 and 2 pi endpoints. And then let's throw all of our critical points in there. I like to put them in order. It doesn't really matter. But I like to put them in sort of numerical order here. So I've got pi over 6. And then I've got pi over 2 would be the next one we would come to. And then I've got 5 pi over 6. And then 3 pi over 2. And you know the drill, but this time we're going to do it without our calculator. So don't pull that calculator out. You can do this. I'll do it with you. So we're just going to plug that in. You're going to need the function on your screen, sine of x plus cosine squared of x. So f of 0, plug it in. Sine 0 plus cosine squared of 0. Okay, let me give myself, I'll just rewrite that. Sine of x plus cosine squared. X is what I'm doing. Sine of 0 is a good old sine of 0. 0. Cosine squared, 0. Cosine of 0 is 1. So I've got 1 squared. 0 plus 1 squared is equal to 1. You still don't have your calculator out, do you? Stop cheating. So sine of pi over 6. That's a short side. Draw it out if you need to. Pi over 6. Right there, I'm looking at the sine value is my height of that triangle. Oops, it's a color I can see. So that's my 1/2. Cosine of pi over 6 then is the long side. That's the radical 3 over 2. And I'm squaring that. So that is 1/2 plus radical 3 squared is 3 over 4. Change that to 2/4 plus 3/4, and I'm getting 5/4 for that. This is fun! F of pi over 2. Sine of pi over 2 plus cosine squared pi over 2. Sine of pi over 2 is my y value at pi over 2. That's 1. That's my height. Cosine of pi over 2 is 0 squared. 1 plus 0 equals 1. Okay, pause the video, calculate the rest of them, and we will pick back up in just a second. Wow, that was a brain workout. Okay, way to get ourselves back mentally in shape. Hopefully you didn't quit on me and you got the rest of the values there. Now we are to the easy part, folks. We calculated all the values, and yes, I know your calculator could have told you all of those. But we're practicing how would we do this without a calculator is really the goal here to figure out. And now we're just figuring out what the maximum and the minimum is. So comparing those y values. So let's see, I've got 1 5/4. That looks like it's my maximum. Interesting, it occurs twice. But remember, when I'm asking for maximum and minimum, I'm asking for a y value. So it doesn't matter that it occurs twice. The highest value that it reaches, the graph just happens to reach that value twice. Unless it asks where does the max occur, and then you would say it occurs at both of those places, pi over 6 and 5 pi over 6. Then you just are going to say what the max is, and it's 5/4. And then we've got the minimum. Is -1. So I would encourage you to take a quick look at the graph here. You could just use your standard trig graph and see what's happening just for a little bit more intuitive understanding. And obviously, if we wanted the whole picture of this graph, we could do our number line analysis and figure out between these critical points, is my derivative positive or negative? Is my function increasing or decreasing? But what I'm trying to show you is the quickest, I know, funny, quickest, easiest way, it really is, to figure out what is because we have a lot of relative maxes. And if you look at this graph, you're going to see there's several peaks. So in order to compare them, we need to compare the y values. So hopefully that helps give you an idea of how to find absolute extrema and a nice way of organizing your work so that you can keep track of what you have.